This is a feedback video, model answer and commentary for component 3 mock, and this is A1, so paper 1 of our selection for this component. We are given a diagram showing an alveolus and its blood supply and some numbers for oxygen and carbon dioxide in various places. So alveolus, so you should recognise alveolus is in the lung, and we've got bronchioles and bronchi, so the air is coming in there. This is a blood vessel, okay, and where has this come from? This has come from the pulmonary artery and from the heart, and it's leaving in the pulmonary vein back to the heart again. Why has blood come here? It's come here to get some oxygen and get rid of carbon dioxide. So that's what should be going through your mind when you first see this diagram, and it's given you a little bit of a close-up here, saying that the blood vessel wall, the capillary wall, has got one layer of cells. The alveolus epithelium has got a layer of cells as well, and there's a layer of water and something called surfactant on the top. So we start off at question 1. A. Name the process by which gases enter and leave the blood from the alveolus. The answer is not gas exchange, that's the whole process by which gases move across from one place to another. And so that's going to be our form of transport from the core, diffusion. So that's from the core. Suggest a value for the amount of carbon dioxide in the alveolus. That's a bit of a naughty word, that amount. But you have to decide what the number is and what the units are. It is a bit of a tricky one, this one. It's a bit of a shock to the system to have to do this and straight away. But we're filling in this bracket here, and we've got carbon dioxide coming in at 5.8 kilopascals and leaving at 5.1 kilopascals. This air and blood, hopefully by the end of the blood's circulation through this alveolus, is going to be at equilibrium in concentration. And if you look at the oxygen 13.3 in the air, 13.3 in the blood, and so we can do the same with carbon dioxide. So the blood is leaving in equilibrium in concentration with the air, which is what we want for the lungs, because the idea is to get the concentrations in the blood different in tune with the air. So we're going to go for 5.1, and we need some units here. It gives us the units, kilopascals, so we're just going to use that. So 5.1 kilopascals. Some people put 5.1, didn't put the units, so don't get the mark. Which of the vessels R and S represent the arterial end of the capillary? Lots of people got this the wrong way around. Blood is going to the lungs with lower oxygen and higher carbon dioxide. So you see there we've got oxygen at 5.3 and then leaving at 13.3. So that's our bit of evidence. So it's R, so vessel R. Give a reason for your choice, because R is low in oxygen, or we could say high in CO2. So that's why blood goes to the lungs, because it's low in oxygen and it's going to get some. Part B. Why do the amounts of oxygen and carbon dioxide remain relatively constant in the alveolus? So here's the alveolus, and it's saying that these tend to stay the same. Well, you'd think they would go down. You think the oxygen would go down and the CO2 would go up, and that indeed does happen, but it seems to magically go back to the same numbers. That is because of ventilation. So the air is constantly being moved into this alveolus and out, in, out when you're breathing. And so we're going to say the proper name for breathing, moving the respiratory medium over the respiratory surface, which is ventilation. So air is replaced by ventilation. Well, you could get away with saying breathing there. What is the function of the surfactant found in the alveolus? So this is the liquid here. The answer isn't so that oxygen can dissolve in it in order to move. In fact, oxygen, the diffusion of oxygen in the liquid is actually slower than it is in the air. It's got another purpose. So this surfactant all around the edge here is there to really to stop this alveolus from collapsing or sticking together. So when you breathe out, these will come into close contact with each other, and quite if they're kind of wet and sticky, they will stick together, and that will give you problems in terms of surface area and so on. So it's to stop them sticking together, or clumping sometimes, and to keep the the surface the surface tension. That we could mention that as well, but I'll stick for the simple answer here. So stop the alveoli sticking together. This next one, sorry, there must be the exam board that this came from must have some sort of thing in the textbook or whatever for this medical use. I apologise, we couldn't really anything sensible here. We would generally give a mark for. The answer in the mark scheme is to do with premature babies who would have a problem with very, very new alveoli sticking together, and so or not producing enough surfactant. But if you said something along the lines that was sensible, then I think we will give you a mark there. So to assist breathing in premature babies, the lungs aren't developed. But in a way, you're not expected to get every single mark on a paper, and that's why the grade boundaries for A and A star are not 100%. They're considerably lower. So don't worry about odd little marks here and there. What we do want you to worry about is graphs like this that show countercurrent flow and parallel flow in fish. You should know these. You should know these inside out. You should be able to recognise these and talk about these. And indeed, many of you could. So, complete the key to show which is blood and water. The solid line is water, and the broken line is blood. And you should know that from these graphs anyway. Which graph shows counter-current flow? That is graph A, where we've got blood flowing one way, doesn't really matter which way we draw it, and water flowing one way and blood flowing the other, whereas on this diagram both are going the same way. Use the graphs to put in the values in arbitrary units. So here they're using this thing called arbitrary units because they don't really care about the units. They don't want to get bogged down in the units. Just really tell us what the numbers are. That's what we want to focus on. and they're doing that for the distance and the amount of oxygen. So don't put in millimeters or micrometers or whatever for the distance. It doesn't matter. Just give us the numbers. The maximum difference between the amount of oxygen in the blood and water. In A, the maximum difference is this on this graph. It stays the same, and at the start it's difference between 1 and 2. So the answer is just 1. In B, the maximum difference, if we look at the start, we have got water at 9 and blood at 1, so the difference is 8. The distance along the gill plate at which exchange is possible. Well, exchange is only going to be possible if the oxygen in the water is higher than the blood. So if the oxygen in the water is higher than the blood, and we can see on graph A, which is countercurrent, the water is always higher than the blood. So we go, how many of these is it along the bottom? So it's all 7 for the distance. So all 7, the water is higher than the blood in oxygen content. Whereas in graph B, it's only from 0 distance to 4 distance that the water oxygen content is higher than the blood. So that's going to be our answer 4. The rest of it they're the same. This, worth noting that on this graph, the solid line and the dotted line, they've put them as close together as they can. They would be in the same place, but it's just difficult to show them on the graph, so they've just shown it slightly below. The maximum amount of oxygen in the blood. Well, which one is blood again? It's the dotted line. What's the maximum that this dotted line gets to on A? And some people have read this wrong off the graph. You need to follow that line. Across, and that when you follow it all the way along, that is 8, where that dotted line hits there. Whereas the maximum for the blood in graph B, well, you could give either answer. You could 5, or technically on this 4.9. So that distance there, 4.9. So either 4.9 or 5. I'm going to write 5. We'll be fine there. Use the information in the table to state which type of flow is more efficient. You should just know this anyway. But it's more efficient in graph A, the counter current flow. So either graph A or counter current flow. So you don't even need to use this information to work that out. You should just know that the counter current flow will be more efficient. And indeed, the next statement, give one reason for your choice. You should have memorized the counter current flow advantages, and you should have said the diffusion occurs over the entire length of the gill. There's always a concentration gradient maintained, and that is diffusion over all 7 there, rather than just 4 there. So we get diffusion gradient for oxygen maintained over the entire length of the gill. And that's question 1.